Have you thought, how does casinos make profit from an inherent randomness in the activities they roll out to customers? Have you thought how a vehicle insurance company decides on the insurance premium rate for a vehicle? Or have you observed that companies with large market capitalization sometimes sees massive growth in the beginning, over time become stagnant and don't see that growth witnessed previously? The answer to all these questions is driven by the fundamental principle of law of large numbers. Suppose there is a random variable x and we know its expected value or the population mean. The law of large number states that as number of trials increases, the observed probability or sample mean approaches the expected value or the population mean. That means if we take a large enough samples, then the sample mean would be closer to the expected value of the population as a whole. We get an intuitive understanding that if we perform enough trials over large samples, the result would be very close to the expected value. But it is often misunderstood why this happens. There is more nuanced depth into the law than it seems from the surface. We have to understand what we are dealing here with. Here, the universe is playing out completely uncertain, random, unbiased, and independent set of events. And by observing these events, we have realized that even though there can be complete uncertainty in the outcome of a particular event, but over a certain period of time, the average outcomes of the events can be predicted. Let us perform a dice throw experiment. Suppose we have an unbiased dice and we are trying to calculate the probability of occurrence of the number 2. Let us throw 100 dice and note the result, and we will call it a one single trial. Suppose x is the number of occurrences of the number 2 from one such trial. Now we know the expected value of x, which is equal to the number of coin tosses within a trial into the probability of success, and that comes around 16.67. So the expected value is 16.67 from one trial for the number 2. Now the law of large number states that if we perform this trial n number of times, the average of the number 2 we get in each trial is going to converge around the value of 16.67 as n approaches infinity, which essentially means that maybe initially this frequency of getting 2s might be much higher or much lower than the value of 16.67, but as the number of trials are increased, we will see that the frequency is slowly converging towards that expected value figure of 16.67. Let us do a small demonstration in Python of the dice throw experiment to validate the law of large numbers. So here I have written a small function that performs 100 dice throws and calculates the number of 2s that has occurred in it, and 100 dice throws constitute one trial. So this function basically gives the number of 2s that has occurred in one trial. So first we will be performing 10 trials, and we will see the results of the number of 2s that are occurring on average. So this is the result of out of 10 trials, these are the specific number of 2s that has occurred, and we get an average value of the number of 2s is 14.8 per 100 dice throw or per single trial, and we know the expected value of 2s is 16.67. so you can clearly see that there is around 10% to 11% less value than the expected value. The sample value is 10% less. That's quite a big number. So what this is as per the expectation line of the law of large numbers, because here the n is very low, we have done only 10 trials, so that is why the results can be uncertain. If we run this again, we might get results that are more than 18 or 19, because or at lower number of trials the results can be unpredictable. But as law of large number says that if the number of trials are much more, it goes towards infinity or it's a huge number, then the results would converge towards the expected value. So now if we have done 100,000 trials, then let's see what the result is. So we can see that the average twos per trial is 16.67. So it is exactly kind of converging towards the expected value, and that is as per the law of large numbers. And we can see from the graph that the value around 16.67 is peaking, has highest frequency. Let us now try to understand how this law works. First of all, we know the expected value of twos count per trial is 16.67. So theoretically, we are expecting twos to occur 16.67 times for every 100 dice throw. Now, suppose like after 500 trials, if my average of twos count say is 10, which is way below the theoretical average, then many people might feel that the law of probability is going to give me a higher frequency in the future trials to make up for the difference. But unfortunately, that's not necessarily going to happen. That's often called the gambler's fallacy. So after 10 trials, as we saw in the Python demonstration, we got an average of 14.8 twos count per trial, and which is like almost 11% lower than the theoretical value. So people can think that somehow the god of probability are going to make it more likely that we will get more twos frequency in the future, that somehow the next couple of trials are going to bring our average up, and that's not necessarily the case. Going forward, the probabilities are always the same. The probabilities are always going to be 0.17 for getting 2. On other hand, it's not like if we had a bunch of 2s to start with, then things would be made up and we would get 2s at a lesser frequency. Law of large numbers reveals that for an unbiased random event, universe doesn't care about its past. Let's say after some finite number of trials, your 2's average count is much higher than the expected value. But the law of large number says that universe doesn't care how many trials has already happened, because we have an infinite number of trials left. So when you average a finite number that averages to high number, and then an infinite number of future trials is already left, the results are always going to converge back over time to the expected value. That's a informal way of describing the law, but it's a very important thing. It's not telling you that if you get quite a high number of twos in the beginning, then the probability of not getting the 2 will increase to make up for the past. What it's telling you is that no matter what happened over a finite number of trials, you have infinite number of trials left, and if you do them enough, it's going to converge back to your expected value. And that's a very important thing to think about. Law of large numbers has application in various fields of analysis, from finance to business. For example, casinos and the lottery every day operate on this principle, because they know that if they do large enough samples, they can calculate how much things can deviate significantly. They understand that if enough people is taken, sure, in the short term few people might beat the house, but over the long term the house is always going to win, because of the parameters of the game that they are making you play. Also, growth rates in finance have a tendency to be a representation of the law of large numbers. This is seen in the form of growth rates over a certain period of time converging around the growth rates of economy. Similarly, is seen in where companies with huge market capitalization more or less become stagnant and don't really see the growth that was observed previously. The gambler's fallacy is a very interesting characteristic of human mind. The human mind always tries to find patterns in every unbiased, independent, or random set of events. We imagine that based on series of events, an outcome is more likely than the odds are actually indicating. That is called as the gambler's fallacy. Human mind has fundamental tendency to find patterns. It avoids randomness and cannot comprehend independent or random events of nature. One interesting aspect of it is the concept of conspiracy theory is fundamentally a psychological construct to counter the phenomenon of randomness. The concept of conspiracy theories gains prominence in human psychology to counter this randomness or the independentness of events. We can observe that whenever in the world there is a string of big events happening which are naturally occurring and independent and random, we find conspiracy theories around them are quite popular, and they come up and those theories actually try to connect all events together with some kind of pattern, and they try to project or imply something. Human thinking cannot grasp this phenomenon, so it feels very uncomfortable when things happen at random without meaning, and when there is no explanation or significance behind set of events that are happening. Rather, human minds feels more comfortable with explanations that can connect the set of events with logic and meaning. For example, if a set of events can be conspired by some unknown entity and events are connected by some dots, and even if the entity is pulling strings from behind for all the happenings, that gives a more stable meaning to the occurrences of things, and human minds can actually feel more comfortable and sane when things can be interpreted in a logical and a meaningful way. In the larger context of life, the idea of supreme power controlling the universe, pulling all the strings, is again a necessary and fundamental construct of human mind to survive and to counter the inherent randomness in nature or the sheer meaninglessness of life.